In this long tutorial about finite element analysis in 2D, we are going to use ID1 plus for nodes X side to simulate a steel plate with the given parameters and values. We have the roller support on the left hand side and at the bottom. So now we create a new functions in 2D, which is based on the side of the plate, the number of elements by x and y directions, Young modulus, and the Poisson ratio and the force vector F. The scale values is the way we multiple the displacement to see it when it's so tiny. And the file names is the export file name when you want to export it later. However, in this tutorial, I'm going to use the figure only. You can do it by yourself. So we know that the number of nodes is the number of element plus 1. So now I declare the number of nodes by x and by y directions. And the number of nodes in total will be nx times by ny. And I declare an array which I will add the boundary node later. For the simulation, I need to know the dx and dy, which will be the length divided on the number of elements by x, and the height divided by the number of elements by y direction. In this FEM 2D, I'm going to use the Gaussian points, which is zeta and eta. At minus plus square root of 1/3. And the weight factor for the Gaussian points is 1. So I declare the vector of displacement U will be the vector with the size of 2 times by n nodes, because we have 2 displacement per node, which is by x direction and by y direction. Similarly, I can declare the matrix of stiffness K will be the matrix with the rank of 2 times by the number of nodes. And the same to the force vector should be 2 by n nodes. Now I try to loop all over all elements to declare the properties and the matrix D for each element. So the first step, I declare the ID of each node of the element. So please remember the scheme of nodes that will be bottom left, top right, bottom right. And respectively, I calculate the global positions of the nodes. Here I declare the local displacement of each node. Actually, I don't calculate it in this example, but in general, you may use it for a faster calculations. And I assign the material property. In this example, we have only one material property because we use only one material. However, in general, you may have few, so therefore you have to assign the material property to each element. And now we try to calculate the linear matrix of stiffness. Because we have only one material, so it should be constant for all other square mesh, all other square element. So I declare a matrix of zeros elements with a rank of 3 by 3, and I change the value of non-zero element to have a matrix which is respective to what I have shown you before. So after calculate all matrix and elements properties, we're going to set the boundary condition to set it up. This is the initialization step in each numerical simulation. So I have to know the node ID to add it to the boundary array. So when I equal to 1, that means the node is at the left hand side of the plate. I fix the x direction, and when j equal to 1, this is the bottom edge. So I fix the y displacement. Now, when the node is on the right hand side, so I apply the force to the node. So it is different for the top and the bottom point, which have only half of the pressure. We know that we assume the force act only at the node, not at the edge of the element. So therefore, we have to times the stress by the length of the element and then divide by 2 for the top and bottom point because it had only one half. For all other nodes, we have to use the full stress. So now I find the flexible nodes by removing the boundary. I set the difference between the array from 1 to 2 times by number of nodes and the ID of the node I have before. In a static simulation, I don't need a time loop. I loop over all the elements once only. So at each step, I'm going to calculate the local matrix of stiffness and then add it up to the global matrix of stiffness. So in each element, I have to loop over all Gaussian points, which is respective to the local zeta and eta I declared before. In the first step, I'm going to calculate dn over d zeta. and dn over d data. Now we calculate the Jacobian matrix. And the dn global will be the inverse matrix of the Jacobian matrix times by dn d local matrix, which we calculated before. And we have to calculate the B matrix, which we derived in the lecture. So in the first step, we calculate the compacted B matrix first, and then part it into the full matrix. In this simulation, I'm going to part it directly. So it's the first row. Now I part the second row. The last row is a combination of the first row and the second row in an inverse order. So now, after calculating the B matrix, I can add it to the local matrix of stiffness. So after calculated the local matrix of stiffness for one element, we add the local matrix of stiffness to the global matrix of stiffness, row by row and column by column. I put it to the next row for your convenience. So now I have to remove the boundaries from the global matrix of stiffness and the global vectors of force. And I got the displacement equal to the inverse matrix of stiffness times by the force vector. And then I add it back to the global matrix of displacement. This is easy because we have done it in the 1D solutions of finite element method. And the force equal to the stiffness times by displacement. In the last step of this example, I'm going to plot it into a figure. So to do that, I have to declare the x and y coordinate array. And now I try to make a mesh grid x, y, which store the coordinate of each node. And the value at each node will be the magnitude of displacement. So I loop over all nodes. I get the node ID and then I set the new coordinate of x and y after deformation. Please time it by the scale so you can see it's because the deformation is so tiny. And I also set the value of the magnitude of displacement at each node. Now I'm ready to plot. So I use the contour F to have a fill contour and I set acid equal so I will have square mesh. I save the functions and try to move to the main screen to declare my problem. So I get L is 0.3 by 0.3. The unit is meter. And the number of nodes here I get is 9 by 9. The Young modulus is a typical steel one, which is 2 times by 10 power 11. And new, I guess it 0.4. For the force vector, I have the pressure by x is 1 times by 10 power 6 and no vertical force vector. So I solve it with the function I just made before. Okay, there's some bug over here. Let's debug it. I forgot a semicolon over here. Save it and run it again. Still the same one. So I forgot something. Okay, so this is the wrong bracket. I should have the square bracket for an array. Run it again. Okay, misspelling. Save it and run it again. Misspelling again. Should be global, not global. Global. Save it and run it again. Okay. I think J shouldn't be capitalized. Should be a small j because this is an indicator. Save it and run it again. Okay, I forgot to increase EID at every time step. Okay, run it again. Wow, it couldn't plot anything because of the same value for any node. So maybe I make something wrong with the D matrix. Yes, I didn't change the indicator, so therefore I changed only value of the element 1, 1. I should change the indicator. So change it respectively to the D matrix in the lecture note. Yeah, I forgot a comma here. Save it and run it again. Wow, I have plotted something here. However, the deformations go by the opposite way. So I have the extension here, but actually it has a compression here. So maybe something wrong with my matrix. I think I changed the size somewhere. My force vector is fine. I don't have any problem with the force vector. So maybe the property vectors. Let's see. Yeah, I think I found it. So the end, the eta has the wrong side. I have to change it back. Well, I have everything is fine now. So the compression and the tension. Please remember that the displacement is time by 10,000 times. So it's extremely large. Thank you and see you next time.